right there. Hello, everyone. So tonight I want to talk a little bit about closure conversion. So closure conversion is essentially the process by which we get rid of lambdas. And so if we think about a program like this, so if we write something like map, so we're going to have map of f over the list L, and I'm going to say if L is empty, then I'm going to be empty as well. Otherwise, I've got a head and a tail, and I'm going to cons f applied to the head, and then map of f to the tail. And so now I can do things like map lambda x is even, or maybe even x over some list. Maybe we can do read, read, read. Okay, so if I run this, let's do 2, 3, and 4. And I get true, false, and true as expected. Um, so the question is, how do we implement lambdas? And the observation is that if I just had defines, if I had defines with no nested defines, then that would look a lot like sort of C-style functions, right? So the issue with nested defines is something like this. So I could have f of x, and then I could have g of y, and this is like plus xy, and now I return g. Now, think about kind of the issue here from the perspective of f, right? Well, this define here is taking this new parameter y, but then it needs to take the value of x that was live at the time that I called f. But here's the really crucial issue. When f returns, right? So if I think about sort of C-style functions, right? When I return from the function, anything that was alive or on the stack or a local variable, like x, for example, in this case for f, anything that was alive throughout the dynamic extent of f or the runtime of f, the invocation of f, when I was actually doing the code for f, well, that's gone after the function f returns. And that's very problematic because I need x. I need x to have some value when I enter the code for G right here. You might say, okay, well, now I return G and I can call G with, let's say, 5. But if the value for X is corrupted, because, for example, we put it on the stack, and then the call to F returned, and then some other code happened, well, now this whole thing doesn't work, right? And so that's kind of why we can't do this in general, right? For example, really, this define right here is really equivalent to this. It's really kind of like an internal lambda. That's how we can think of it. And in fact, we could think of everything being in terms of lambdas just at the top level if we wanted as well. But I think we want to stick with defines. And we want to basically say that our primitive understanding of what it means to be a program is that we're going to want to have a bunch of these top level defines. And in the project, we even have like a top level define called main, which is just kind of the main piece of code. And the idea is that the code is really invoking main as the first thing it does. Now, of course, there's never a call to main in the code that we emit because that's just kind of the standard part of the operating system's way that it runs, binaries, right? Is that there's a main function and then we get jumped to by the OS loader. Okay, so the question though is how do we get rid of these lambdas? So if it were something like, let's say in this case, right? In this case, it's actually pretty easy because I could write an is even function that takes x as an argument, and I just return even right here. And now I can say map is even over this list And no issue there. Nothing's hard at all, right? That's all very natural. And at runtime, this is a pointer to the function for is even, for example. That's the way that we could think of it, things like that. Um, and so is it just as simple as that? Is it just as simple as taking every lambda and putting it at the top level? Well, the answer is unfortunately no, in general. Um, and so let's see why. Let's think about this thing right here. Let's say that I wanted to map, let's say lambda x and then lambda y and then plus x y, except I wanted to take this whole sub-expression, right? Because this is lambda x and then it returns a lambda y, so that doesn't work out for the argument to map. But let's say I take this whole thing and I apply it to like 23. Well, now, this thing is a function right here that at runtime is really this lambda because it's the result of applying this lambda to 23. And then that has the effect of instantiating x to be 23. And we return this lambda y right here. So let's say we tried to do the trick from last time where we just say, okay, well, every lambda is going to get a name and it's going to get lifted to be a define. So let's say we did that trick. Let's say this is, we're going to call this our internal lambda. So let's say define inner lambda, and its argument is y. Notice it's got one argument here. And the code for it is x plus y. And then here we're going to have inner lambda. Um, and now, of course, let's try to hit run and see what happens. Well, and now this doesn't work. And the reason it doesn't work is because right here in inner lambda, this variable x is not available, right? So how do we get that to work? That's going to be really the central question we need to address here. All right, so the basic tension here is that x is not in scope. Okay, so previously when we had this lambda sitting right here, x was in scope by virtue of the fact that the lambda was nested under this other lambda. But when we have the functions as all top-level functions, that doesn't work, right? Now, when we do have nested function definitions, we get a very similar thing, right? In fact, it's the exact same kind of problem. Um, and so the question is, how do we handle this? And the observation is basically this. The observation is that we're going to take everything that would be a lambda, and instead we're going to lift it. So this phase is called lambda lifting. We're going to lift it to instead talk about closures. And so a closure, so a closure is code plus data. In particular, it's a function pointer to a C-style function with parameters, along with an assignment for all free variables. And in this case, the free variables are x, right? If we knew what x was, or if we had x in scope, then everything here would be fine, right? But we don't have x in scope. And so what we have to do is we have to throw in an extra argument to this function. And so here's what we're going to do. We lifted this inner lambda, and in lifting it, we take the parameters, in this case, just y, and add a special clo parameter. In this case, I'm just going to make it the first parameter. But it doesn't really matter. Could be the last, could be the first. It just has to be something that the caller and the callee agree upon. And then the special thing is that to actually call this inner lambda, Well, now we're going to have to provide the closure as an argument. Okay, so we're jumping the gun a little bit here. So I said that this lambda y, so now this is the inner lambda. I've got my variable y here, and I've got my closure. In this case, my closures, I'm going to I'm going to make them vectors. So my closures will be vectors. If there are n free variables, in this case, there's one, there's x, that's the only free variable here. Then we put them in just some canonical order, right? So we could sort them or just put some order, put them in any arbitrary order, right? And then what we're going to do is then every time we would return a lambda, we actually allocate a closure. Closures will have the following structure. They're going to be a vector. And the function pointer is going to be the first element of the vector. And then the first variable, the first free variable, will be the second thing in the vector. The second free variable will be the third thing in the vector, and so on for all the free variables. And so when I'm called, so first of all, I guess I should, I'm going to have to fix up a little bit of stuff here to get a definition of x, which I'm going to need to pull out of Clo. I'm also going to need to change up this place right here because I said that everywhere I return a lambda, I'm actually going to allocate a closure. So in this case, I'm going to do vector, and now I'm just going to do inner lambda because I've taken this thing and I've lifted it out to the top level. And now I'm going to capture the variable x. In this case, x is the only free variable. And so my closure for this lambda will include just inner lambda, the actual code pointer that corresponded to this lambda, and the variable x, which is the only free variable that was captured. Now, that still does not solve my problem. I have a few other kind of things that are going to happen here. So the first is this. The first is that I still don't have a binding for x here. So let's fix that. So inside the lifted lambda, I need to know that free variables from the lambda will be stored in canonical order in the closure Clo. In other words, I can get x by doing vector f Clo of 1. Notice it's not Clo of 0 because Clo of 0 is always going to hold a function pointer. And so the idea is that whenever a user actually invokes inner lambda, they're always going to pass that closure as the 0th argument. And then whatever values they would actually be calling the function with will be the rest of the arguments. Okay? Now, so let me just do that. I'm going to make a let here, and I'm going to say let x be vector f Clo of 1. Then I'm going to return the addition of x and y. Okay, so now that's fine. Okay, but there's another thing that's going to happen here because now I've got multiple lambdas, right? So let's do sort of the main lambda. So we're going to lift this lambda now too. So let's call this maybe outer lambda. So let's call this outer lambda. And it's going to have a closure argument too. Now, in this case, the outer lambda, this lambda here doesn't actually have any free variables. And so maybe we could get rid of it, but maybe we don't want to get rid of it because if we do get rid of it, then we need to know in our compiler when and when we don't have to hack on this extra closure parameter. And so the easiest thing to do is actually going to be to say that just basically every function in our program is going to have an extra closure parameter, except for maybe one function, and that's main. The reason that main is not going to have a closure parameter is just that main is invoked by the operating system, and the operating system doesn't know how to construct our kinds of closures. And so we're just going to treat main a little bit special, I guess I would say. Okay, so we've got our outer lambda here. Like I said, we're going to have this bogus closure parameter, but then we're also going to accept x. That's our outer lambda. And then we are going to take this. Now, here is where if this lambda had free variables, we would bind them by looking them up in CLO. It doesn't, so we're just not going to do that. So here, I'm going to replace this lambda with a lambda allocation by saying vector of outer lambda, and then all of the free variables. In this case, there are no free variables. And so I'm just going to have it as this vector with just a function pointer in this case. Now, this code is obviously wrong. The reason it's obviously wrong is as follows. We have not fixed up call sites to our closures, right? So right here, I lifted this to have this closure representation. But if I do this, I'm also going to have to make sure that when I actually apply closures, I do that in a special way too. All right, so here's what I'm going to do. So this is my closure right here. Let's let bind that. I'm going to call that my closure. And in this case, the closure consists of more than just the function that I want to call. So it's not valid to call, I can't say vector of something right here. That's just a type error in Racket, right? That just doesn't work. Okay. And so instead, what I have to do is I have to make it so that when I actually do this application, I have a function pointer here. And I'm going to get that by taking this closure and then extracting it by saying this is going to be vector ref clo of 0. Now here I can call f on 23. Now, this is almost correct, except I made a little bit of mistake here. So if you remember, when I defined all of my little lambda functions that I lifted, I didn't just have this function 23 here. I also had the closure itself as an argument. So I need to be passing that too. And then there's another thing which is going to happen, which is that up here in map, I'm also going to need to make sure that when I invoke the function, so previously I had f of head right here, and that was the result. Now I can't have f of head because f is actually a vector, or sorry, is actually, well, it is a vector, but it's actually a closure. And so I'm going to say, maybe I'll call it my f, or like the closures f is going to be vector ref f of 0. And now I'm going to call that f, and I'm going to pass in the closure as the first argument. Not that. I'm going to pass in vector ref f0 as the first argument. And then I'm going to pass in head, which was the previous first argument, because I actually wanted to call here, this was f applied on head, right? And so this is actually f. So to get the function pointer to f, I extract it from the closure by vector refing 0 from it. And then because I expect that it has been lifted and thus has this convention where clo is its first argument, I'm going to pass that, I'm going to pass the closure, which is actually just f, not vector ref f0, because vector ref f0 is a function pointer where f is the whole closure. Then I'm going to apply that to head. Okay, and I think this should work. So let's see how this works now. So what are we expecting that the value is going to be? We're expecting it's going to add 23 to everything in the list. So let's see. Okay, so 1, 2, 3. And it worked. Nice. Okay, great. I'm really kind of surprised it worked. Um, okay, so this is the style. So how do we do this? How do we do this systematically, right? So if I've got something like define f of x, y, if I've got like lambda a, b, lambda c, d, lambda e, f, and so on. Maybe this is like a big expression that adds all of them up. Okay, so let's do some more practice. So I'm going to do closure conversion bottom up. What I mean by that is I'm going to start with the sort of innermost lambda, and then I'm going to basically take this, I'm going to lift it up out of the program. That's why they call it lambda lifting, right? So let's take this and give it a name. So let's call it like lam78, and that's this thing. And then I am going to lift it to a define. And so I will take this little lambda away and make EF parameters. And then I'll add clo as a parameter for this. And now I'm going to look at all the free variables here. So if I look at the free variables in this body, I can see it's A, B, C, D, not EF, but then X, Y. Okay, so now let's just order them. Let's just canonicalize the order of those variables, and let's just say it's going to be A, B, C, D, X, Y. The reason that that's important is because over here, when I allocate vector lam78, I'm going to need to respect this order as well so that they actually match up. Okay, so now here I go. And the question is, how do I get definitions for all these free vars? And the answer is that I generate a big let block. And so I'm going to say let A be vector ref clo1, because remember clo0 has the function pointer. And so first in the canonical order is A, but that also means that when we allocate a vector, or sorry, when we allocate the closure over here, we have to pass in A first. Okay, so I think you get it now. A goes first. And then let's actually just use let star so that the text doesn't go way to the side of the page. So B is going to be vector ref flow 2. C is going to be vector ref flow 3. D is going to be vector ref clo 4. X is going to be vector ref clo 5. And Y is going to be vector ref clo 6. And now I've got all my variables in scope. E and F come from the binding right here, and so I don't need to put those as free variables, and that is all good. Okay, good. So that's it for that one. But remember, it's bottom up. So I went to the sort of innermost one. That's what it means to process a tree in sort of bottom up fashion, is that you sort of go to the bottom first, start processing that, and then you work your way up top. So here I've got the sort of innermost lambda, which I called lambda 78. Let's take this one right here, and let's say this is going to be, so now let's say define lam 43. And that's going to be C and D are going to be my arguments. And now what are my free vars? So I need a canonical free vars ordering, and that's going to be A, B, no C and D, because those are arguments, and then X, Y. Okay, so now let's do let star. Then A is going to be vector F. I need clo as an argument, of course, here, so I can actually have the closure to get the information from. B is going to be vector ref clo of 1. X is going to be vector ref clo of 2, and then Y is going to be vector ref clo of 3. Okay, and then everything else stays the same, except for here, I'm going to do vector of lam 43. And now I need to pass in the free vars, which are going to be A, B, X, and Y. So there we go. Got that. Okay, so you see now I've lifted the first two and it's bottom up, right? So, as I process the lambdas from the innermost one, I replace the innermost lambdas by allocations of closures and rewrite those. And so when I do a little bit of lifting from a sort of a lower level, sort of bottom position up to the top, that makes the sort of total sort of depth of lambdas in my program smaller. And so I'm kind of constantly, I'm always decreasing that depth until I don't have any more left. And so eventually this process kind of runs out and hits a fixed point. Um, and now I'm at my final one. And so let's call this, let's just say this is define lam 57. And then this is going to be A, B. And then this is going to be, so I need some free vars. So my canonical free vars order is going to be X, Y. And those are the only ones I need here. So my X is going to be vector ref close 0. Y is going to be vector ref close 1. Okay, there we go. And I've got A and B as arguments. And now here it's just as simple as vector of lam 57. And now it's just X and Y, and that's all. There we go. Great. Okay. So that's how we would translate that whole expression, right? So let's see, what was the original term? The original term was define f of x, y, and then it was lambda a, b, lambda c, d, and then lambda e, f is the inner one. And then like plus a, b is this expression right here. All right, so that's how we would sort of closure convert a big chain of lambdas, something like this. So now the question is, if we actually wanted to call this in our new form, so now that we've closure converted it manually, if we actually wanted to affect this call, right? So if we have something like this won't work anymore. We've got to translate it to use our style, right? And in fact, we should be adding a closure here as well. So here I'm going to do a vector f 0 and 1, and that's going to give us, let's say, f plus. F plus is going to be this whole quantity right here. Except notice that this F plus is actually a closure. And so instead of doing this, we want to say this is like clo of F, right? The result of applying this inner F, we get a clo. And so now the actual F pointer is going to be vector F, clo F of 0. And that's how we get the actual function pointer. Here we're going to call fptr. We're going to pass clo_f as our argument. And that's going to give us this sub-expression. We're applying this on 4,5. So let's call this like clo f, or let's call this like f ptr plus. And I'm going to have this second one and call this like clo f plus. And then this is the result of this thing here. And I'm going to say fptr plus is going to be vector f of clo f plus 0. And then I've got f pointer plus clo f plus that's going here. Okay, so that's all good. Now this thing, let's say this is clo f plus plus. Now I'm going to have a let star. I'll do that in a second. And then I'm going to have my f pointer plus plus. I'm going to pass in clo f plus plus with 6, 7. There we go. And let's see. Ooh. That's very unfortunate. Didn't work. Ooh, here's where I messed up. Okay, so I made a mistake. I meant this to be 1, 2, 3, and 4, and then this should have been 1, and then this should have been 2. So I made a mistake there. And oopsie. There we go. Select, let's see. So I've got plus 1, 2, 3, 4, 5, 6, 7. And yep, that's correct. Okay, so yeah, that's how we do it. So nice. We figured that one out. All right. So we've talked about how to, manually do the closure conversion process. Now let's talk about how to systematically do the closure conversion process. And by systematically, I mean we want to write a function C-E that accepts an expression E and spits out basically a closure converted version of it. And so, I think, the best way to do this is kind of a great example of when we might want to actually use mutability. And so I'm going to just say there's going to be a variable emitted defines, which is going to be the empty set. So we're going to initialize emitted defines to the empty set. And then I'm going to say there's going to be a new helper function called emit block bang, or let's call it emit define bang. And let's say we're going to do set bang of emitted defines to be set add of emitted defines and this definition defen. Okay. So that's a little helper function. And then I'm going to make another helper function. Let's call it, so this is going to be like closure convert E. And I'm going to make this helper function C of E. And it's going to get run on every sub-expression. And the interesting cases are applications and lambdas. So when I'm at a lambda, first of all, let's just see if this works at all. Okay, I need to call C of E on E. And then let's return this and emitted defines as our answer. We're going to do closure convert of plus 1, 2. And as expected, that just returns plus 1, 2. But if I do closure convert of lambda x, y, z, apply, let's see, let's just return x, and we're going to apply that to 1, 2, 3. And in our case here, I've got a special app form that helps me recognize sort of tagged application that's distinguished from application of built-ins. So I'm going to assume that there's been some previous pass in the compiler. In our class compiler, this is the case. But if not, you could do some pass that would rewrite applications to this sort of a form. And in this case, it's going to be to do. Okay. So now the question is, what do I do with both these forms? I'm going to move app down here, actually. So now the question is, how do I actually do the lambda lifting? And so when I'm at a lambda, what I want is, so the first steps are calculate the free variables of e body minus x's, right? And then put free vars in some canonical order. And then I'm going to generate a define with some new name, like let's say lam123, and then my x's. Except I'm also going to have this special clo argument here. And then in eBody, unpack the free vars in canonical order. Unpack the free vars in canonical order so that I can use them in eBody. And I think that's basically it. And then I guess 5 is emit the define. And then I guess now return vector of lam123 and then the free vars in canonical order. Free var 0 and so on. Okay, so then this is the step where I actually build, allocate the closure. Okay, so let's just start doing it. So I'm going to say free vars are going to be, so I'm going to call them, let's say FV is going to be free vars, and I've already written this function up here, free vars of E. This outer function that's being matched on will handle all the work of considering the x's to be part of the arguments and then removing them from the free variables. And let's say canonical vars is going to be set to list of fv. Put fv in some arbitrary order. The order doesn't matter. It just has to be some arbitrary order. And then I'm going to say new top level defin is going to be define of f, where f is going to be a new Jinsen, of lamb. And then I'm gonna have clo as my argument. And then I'm gonna have my x's, which come from right here. And then I want those spliced in. So I'm gonna say x's, that's my define. And then I'm going to closure convert the body expression here. That's my new top level definition. Except in my new top level definition, I want to, so let's say I'm going to call, let's do unpack free vars. This is a new function, a new helper function I'm going to write. And it's going to take two arguments, and it's going to take the canonical, it's going to take the variables in some canonical order as a list, and then it's going to take the basically body that I want to stick in as the body of this define. And unpack free vars is just going to be a simple recursive function that's going to match on rest of canonical vars. And when it's empty, I'm going to drop in the body. Otherwise, I've got a head and I've got a tail. And I'm going to generate a let. And I'm going to say let head be, and now I need, and ooh, I've messed up because I actually need another definition here. I need an index that I'm incrementing. And so here I'm going to add another variable in. I'm going to make it start at 1 because here I want to be able to do vector ref clo. Notice that I'm not unquoting this. The reason I'm not unquoting it is just because I'm going to hard code it to be the name clo. I'm hacking it in right here as the argument to the definition f. It's always going to be the first argument. I'm going to need to remember that when I do applications. So I'm going to do vector f of clo and then in. And then in the body here, I'm going to generate a call to unpack free vars of rest canonical vars. And then I'm going to add 1 to n. All right. And then I think that's everything I need. That's my new top level definition. I'm going to emit the define. So I'm going to say emit define new top level defin. And then I'm going to return a little block. I'm just going to allocate a vector. So let's call it, I'm going to use gensim here. Let's define v to be gensim. Now, I guess we could just say vector of f and then, basically all of the canonical vars. We'd like to just do this. Essentially, that's what we would want. Except at this stage in the compiler, in my class, I've actually gotten rid of a vector and I've turned it into basically vector set bangs and make vectors. And so instead, I'm going to do this. I'm going to say define v to be a gensim of vec. And then I'm going to say let v be make vector of how much space do I need? I need 1 space for the function pointer. And then I need length of canonical vars spaces for all of the canonical, all the variables in some canonical order. And then I'm going to basically pack canonical vars 1. And then here I'm going to pass in, I guess I don't need to pass in f. So this is going to be another helper function that's going to do the analog of unpacking the variables, it's going to pack the variables. So I'm going to say pack canonical vars. And here I'm going to say rest canonical vars in. And I'm going to match rest canonical vars. And if it's empty, then I'm going to say this is just going to be v. So I'm going to return the actual vector at the very bottom where I actually bottom out. The final body of this big let stack will be return this v, where that's the actual allocated vector. Otherwise, I'm going to say let nothing be vector set bang of v at index n to be head of the rest of the canonical vars. So this is head dot tail, and I'm returning this let, and it's head, and then I'm calling pack canonical vars with tail and plus n1. Okay, there we go. So that's the whole case for Lambda, I think. Let's test it out. Okay. So first, what is EF? I think this is actually convert F. This is CE, convert expression. Okay. And now let's do closure convert of lambda x return x. Okay. And ooh, I made a mistake. Here, when I did the actual allocation of the closure, I should also be setting I should be doing vector set bang of v, and I should be setting the 0 slot to be this f that I just allocated. Okay, there we go. Okay, so now closure convert lambda x x, and there we go. I've got this top level definition, lam 658179, which takes clo x and x. That looks right. And then my main top level definition that I write says allocate this vector, do a vector set bang of 0 into this, and then return that vector. Okay, so that's all good. Let's try something more complicated. So let's do closure convert. Let's do closure convert of lambda x, y, z. And then lambda x, y, and then plus x plus y, z. Okay. And then let's pretty print the result. I feel like we've made a mistake. Oh, yeah, of course we've made a mistake. We just didn't call it with the right thing. Here we go. pretty print, and then this result here. There we go. Okay, yeah. So here, I allocate a single space for the variable x. Oh no, excuse me. I allocate a space for the variable z because z is the free variable here, of course. And there we go. That looks right to me as well. And then the top level says to just make this lambda. There's no free variables, so that's all expected. Okay, so that looks good to me. So looks like lambdas look mostly correct. Now we need to fix up applications. Okay, so in application, assume EF evaluates to a closure. Now let bind the function pointer and evaluate it on eargs. Okay, so what we're going to do is we're going to say let, we're going to say fptr is going to be a gensim. And then I'm going to say let the function pointer, or let the function pointer, actually, let's just say, maybe we can say vector ref ef 0. No, I think we actually want to let bind the closure as well. The reason is that we don't want to evaluate EF twice, because what if it contains side effects? We only want to execute it once. So let's do closure. And this is going to be the closure. And I'm going to say, let clo be EF. And then let fptr be vector ref clo of 0. And then I'm going to app fptr on clo, and then the rest of my eargs. And I'm going to splice those in. Okay, and I think that's just it. Okay. So there we go. Now if I do convert or closure convert of lambda x y lambda a b plus xy plus a b. And then let's do 1, 2, and then actually I think we want to use app here. And then app 3, 4. I think I haven't closure converted the sub expressions. So that was the problem. And then here I need to map convert closure across all the arguments. So that was a mistake. Okay, so that was a mistake. Fix that. There we go. Awesome. Okay. Here we go. So our top level expression is going to say the outer is going to be apply the function pointer with some clo. Ooh, that's not good. Didn't unquote there. Okay, so there we go. So here we go. Good. It's okay that I've got clo here. I am just kind of following that convention. There's nothing wrong with it. I guess as long as the user doesn't use the name clo. So that's something to think about. Okay. So this is basically how you do it. I will leave a link to my code up on the YouTube video, but this is the process. Now this is this is just the bottom up mechanism for closure conversion. To me, this one makes the most sense. You're just kind of walking over the term. It's also a really great use of mutability. There's no issue with mutability here, in my opinion. You could restructure the code to use like monads or something like that, but in this case, I don't think that would really be useful. I think it's actually more clear to write it in this just sort of naturally um, mutable style. As you're emitting defines, none of those defines clash with each other in any way. They're all kind of orthogonal. So it's just a very simple use of mutability, in my opinion. It would be a little bit trickier, although not too much harder if you use the right techniques to refactor this to use sort of a more pure functional style. But yeah, that's the algorithm for closure conversion, which is a major part of basically how do you do, in a systematic fashion, how do you do the sort of lambda lifting that we did over here manually. And in a compiler, for example, in my CIS 531 class this semester, if you're interested in doing the closure conversion aspect of the problem or the most recent project, I really recommend following basically this code right here. So if I find any bugs in it, I'll update the code online, look at my reference solution, and make sure I didn't miss anything. But thanks so much for tuning in tonight. Certainly a complex topic, but a really fun one because it makes you realize that you can get lambdas just for free if you do this nice little lifting process and just turn them into top level finds plus closure allocations. All right, thank you.